In this series of videos, we will discuss principles related to digital imaging processing, which is the computer processes applied to a digital image to optimize the appearance. Many of the functions are performed automatically and go unnoticed when processing a radiographic image. The first topic I want to cover is what is a histogram and how it is created. A histogram is a graph representing the raw data within a radiographic image. The data that is represented in the graph is the pixel values. Each image is made up of many pixels, and each pixel is assigned a value of brightness. I like to think of it in terms of shades of gray. Just from looking at an X-ray image, we know that there are bright white areas, light gray, medium grays, dark grays, and black throughout our image. The histogram represents the incidence of the values of grays or intensity within a graph. The x-axis of the graph represents the value of the pixel, or the shade of gray. We could also describe this as the pixel intensity or level of exposure. The y-axis is the number of incidents for that value, so basically the number of pixels having that value of gray or intensity that is demonstrated within the image's raw data. When the computer is creating the histogram, software determines where the collimated border is located and excludes data outside this area. The computer also determines where the pitch black areas of unattenuated beam are located in order to exclude that data in the histogram rescaling, which we will talk about later in another video. The histogram is constructed by counting the number of pixels within the image at each brightness level. In CR, the entire plate is scanned, and from this information the histogram is derived. In direct digital radiography, only the area of exposure is included in the histogram. Because of this, the histogram for CR and DR of the same part and collimation may appear slightly different. Histogram errors are more likely with computed radiography because of errors that can happen with detecting the collimated borders. Get ready to pause the video shortly so that we can create a simple histogram together. What I want you to do is count the number of pixels for each level of brightness within this representation of a radiographic image. Graph the information on the worksheet provided. Use a pencil and write lightly in case you make mistakes. The worksheet is located on D2L. Note, this example is extremely simplified and is meant to give you a working idea of what the computer calculates nearly instantly. So at this time, go ahead and pause the video and complete the worksheet. Please make sure to complete the worksheet before continuing with the video. Your graph should appear something like this. The x-axis represents the value of intensity or level of gray, and the y-axis was the number of pixels that had the value. Hopefully yours appeared similar. If you have any questions about this, please see an instructor to make sure that you understand this concept. A histogram will include all pixel values within the collimated border of the radiographic image. The values include those representing anatomy of interest and may also include values representing areas within the collimated borders that anatomy is not located and the X-ray beam directly interacts with the image receptor. It may also include values representing a barium bolus or metal prosthesis. Within the histogram, 2 points are marked to designate the volume of interest, or VOI. The S-min, sometimes called S1, is the lowest border of the volume of interest located on the left side of the histogram, and the S-max, or S2, is the highest border of volume of interest located on the right side of the histogram. Any values between these two values are included within the volume of interest. This area is what the exposure indicator, or EI, is based on. The exposure indicator is a numerical value that indicates to the technologist the level of radiation exposure at the image receptor. Technologists can utilize this number in the process of determining if the exposure factors they chose were ideal for that image. There are areas outside the VOI that are included in the histogram that represent pixel values that are not within the anatomy of interest. For example, we see a spike to the right. This is representing values where the X-ray directly interacted with the image receptor and did not contribute to the valuable information of the VOI, and therefore they are excluded when calculating the EI. There are 3 types of histograms that we will look at. There's a type for different expected exposure configurations. Type 1 histogram expects that the histogram will have a spike on the right. As stated earlier, this represents the area on the IR that was within the collimated border but outside of the anatomy. This was direct exposure to the IR and is commonly seen on the histograms of extremity projections. A type 2 histogram typically occurs when there is no direct exposure to the image receptor, meaning the anatomy covers the field of view, such as an abdomen radiograph. Notice there is no spike on this histogram. The third type of histogram has a spike of bright pixel values on the left side of the histogram. This is representative of something difficult to penetrate within the collimated border. It could be a bolus of barium or a metal prosthesis that is attenuating the X-rays and not allowing them to interact with the image receptor in that area. The S-min is located to the right of this spike. In review, histograms are graphs that represent the number of pixel values for each exposure or intensity level. The volume of interest is the portion of the histogram data that is between the S-min and the S-max. It represents the data set that is the anatomy of interest on the radiograph. The exposure indicator, or EI, is the level of radiation exposure to the image receptor and assists the technologist in determining the appropriateness of the technical factors selected.